be somewhere else.
I got lost.
I don't understand. I mean, this is like half the class. I mean, this class is supposed to have 60 people.
They're out picking another processor.
Food processor.
It's the best kind.
Wrong. That's the brand to get. All right. So tonight's lab is going to be the same thing. So if you're done with this lab, there's no need to attend the lab for the late lab people. Or you can go to the lab and we can talk about the processor stuff. You can play with the processor and whatnot. So that's up to you. But next week we'll have new activities that are going to be designed around the processor. So we'll start to have some fun stuff to do. All right. And let me close this. I think Logisim has crashed. So I'm going to have to restart that. It's not unusual. Logisim definitely has bugs, and I have not had the time to fix those things yet. It is open source, so it's technically possible and encouraged that we go in and fix all the bugs, but I just haven't gotten the time yet.
Isn't it unmaintained though?
It may be unmaintained, but anyone can pick it up and just go, okay, I'm going to be the.
But then how do you have a release?
Sorry?
I mean, I guess you could build it yourself, but then
the Java files are inside the jar file.
Yeah.
The jar file, when you unzip, it actually includes all the source files.
Yeah. Never mind.
Yeah, so you can use any Java compiler to compile those, the source code back into bytecode and reproduce the whole thing. Yeah, so you can either use a GitHub or get what is the other one? GitHub versus GitLab. Yeah, you can just push it that way. Yeah.
Well, I don't know. I guess you'd have to maintain a fork of it.
Right. Yep. So it'll be a fork of it.
If you do that, you want to add high DPI support because it sucks on a 4K screen.
I do use a 4K screen at home.
Something to think about.
How does it suck on a 4K screen?
Huh?
How does it suck?
Okay, the text is like that big. It's
Yeah.
like 3 pixels high, and I can't comprehend what it says. I can imagine what letters they are, but they're.
But that has to do with your the resolution of your screen because your pixels are just too small.
But I don't want to drop my resolution for. It doesn't properly scale with Windows.
Yeah, because Windows has built-in scaling.
Oh,
so you can change the scaling.
Gotcha. So it doesn't play with that. Okay,
Yeah, so you can
gotcha.
have like 4K resolution. And scaling
Understood.
300%.
Okay.
That's all I'm saying.
All right. So we are back to the processor. So what we'll do today is we'll take a few instructions. We'll take a look at a few instructions, and then as we execute those instructions, we'll kind of look at how the paths are established between the components and how things are getting done that particular way. So before we do that, we first have to understand what are the registers, where the registers are located, how they are called, and stuff like that. So within the register bank, this is the inside of a register bank. These 4 registers, A, B, C, and D, these are what we call the software accessible general purpose registers. Otherwise just known as just registers, okay? But they are called A, B, C, and D, and you can specify these registers in many instructions that we have for this particular processor. So is that part okay? Some of the other registers are not directly accessible in software. You cannot specify and go like, I want that register. No, many of those other registers are not accessible in software. Okay, but these 4 are specifically accessible from software. So when you look at this diagram, okay, you can see there's a 8-bit input pin right here. Okay, let me go back to the selection tool. So here we have a 8-bit input pin. It is labeled REGIN for register in. We have a REGIN cell, and this is a 2-bit input pin, and it goes through a decoder So that this way, out of the decoder, we can basically enable one of the 4 registers. And that's the purpose of a decoder. In case you do not remember, a decoder is like a demultiplexer with a 1 as a constant input. So in this case, the selection allows us to say, okay, which one of these output wires do we want to be a 1? Do we want 0, 0 to be a 1, 0, 1, 1, 0, or 1, 1 to be a 1? Is that okay? So it basically specifies which register is going to be updated. That's the job of this particular pin. On the outside part, we have 2 multiplexers. One multiplexer for each output pin. So here's another multiplexer for the other output pin. Each one has its own select. In other words, the output of this particular multiplexer is independent to the output of the other multiplexer. They are completely independent. You can have both of those to choose the same register if you want to, but you can also choose to have different registers. Is that okay? So do we understand the operation of the register bank itself? Yep.
So what you're saying is you can read 2 registers at the same time?
You can, yes, you can utilize the content of 2 registers at the same time, and you get to choose which 2 registers. But those quote-unquote 2 registers can be the same as well. So each one is independent to the other one. You have 4 choices for each of the output of the register bank itself. Yep.
The registers hold what?
Say that one.
What did the registers hold?
The registers they basically store values that you need to process, like numbers that you're adding, numbers that you're subtracting, but they're also used to store the result of the addition, subtraction, and stuff like that. Mostly. Okay. So are we okay with this picture? Are there any questions about the register bank itself? Yep.
So when you're coding, you type, like earlier, you're using pointers and you're using the addresses, that's basically like what register you're
No, we're not going to use addresses. Well, okay, we do have addresses, but when we use addresses, we are accessing RAM. So addresses only make sense when you're accessing RAM. When you're accessing registers, you just designate the register as A, B, C, or D. Okay. So, but is this picture okay? Do we understand, what the decoder is doing, what the multiplexers are doing, and how we can choose which register to update, or choose which register to be output 0, and choose which register is output 1. Okay, so here's the full name. This is register output 0 of the bank itself. This is register output of the bank itself. So the entire register bank only has 2 outputs and 1 single input. But inside the register bank, we have 4 registers. Is that okay? All right? Okay. So if this is okay, we go back to main, okay, the really ugly, complicated, output here. And then we'll go take a look at some of the instructions. To be more specific, we're going to look at one specific instruction called CPR, which is not the CPR that you know of. CPR in this case, represents copy register. Okay, so I'm just paging down to get to the point of where I want, right here. And then we'll change the zoom a little bit so it shows a little bit better on the screen. 150% should be good. There we go. So the CPR instruction is right here. It belongs to the copying type of instructions, because I try to categorize the instructions into multiple categories so that we can just kind of go like, okay, these things are doing something similar, and those are all kind of bundled together. So CPR has this format, okay? So when you type, this is called what we call a mnemonic. A mnemonic is basically a name that you can use to refer to an opcode, okay? And then you can specify the 2 registers. In this case, register X is the destination. The first operand is always the destination. So register X is the destination, Y is called the source, and then on the right-hand side, after the // this is what it looks like if I were to describe it in C and C++ syntax. Okay, whatever Y has, X now has the same content. So are we okay so far with the notation? Now X itself is a register, Y is also a register. Each one can be A, B, C, or D. Is that okay? All right? Okay. So if that is okay, then we can go to the assembler. And I think right next door, this is the assembler. And in the assembler, you can specify your program in the source tab, okay, in the source sheet. This is where you specify the instruction. And let me delete the code that I have here already, and just delete. So one thing, just one warning: do not change column B. Okay, don't delete anything in column B. Don't overwrite any content in column B, because column B contains the error messages or the spreadsheet code to give you the error messages. If you mess around with column B, then you may not see error messages when there are actual error messages. Okay, so we delete all of this stuff here, and then we'll try a few things. Okay, since we're here. First of all, let me magnify just a little bit, 125%. And I'll just type CPR by itself. Okay, in fact, I'll type CPRR, which is the incorrect mnemonic. Okay, and after a moment, it says it's an unknown mnemonic. So that's why I tell you do not modify anything in column B, because column B has the code to give you any type of error message. So if I say CPR, it is a known mnemonic, but then it says, hey, register X is expected, register Y is expected. In other words, I'm not telling it which register is the destination and which register is the source. So if I give it something that is not reasonable, because we don't have a register E or F, it will still complain. Okay, so it's still going to be complaining, maybe the same message. Okay, because X has to be A, B, C, or D, and then register Y also has to be A, B, C, or D. So I'm going to fix this and say CPR A, B. Okay, so now the error message should go away. There we go. And this is a valid instruction. Is that okay? What is this instruction representing? Well, it's representing a opcode, OPCODE, which is a binary bit pattern that the processor natively understands and go like, oh, you want to copy register B to register A. But we are not seeing the binary bit pattern here, are we? So now the question is, okay, so where do we find the binary bit pattern? How do we know what it should look like as the binary bit pattern? In the shared folder under processor, there's another spreadsheet. I think I have kept it here. It's called opcode table. Okay, you don't have to go there. I'm just going to open it so that you know where to find it. So opcode table is designed for people to read. This is not a spreadsheet for the computer to do something autonomously. So when you look up this one, you can look up the instruction that we are talking about, which is CPR. So we can search for that. You can see my computer is really slow. And I've closed a lot of the other stuff already. Okay, come on. Okay, do we see CPR? Yep, here's CPR. Let me magnify it so that we can all see that particular row. Okay, we should be there soon. Or did I pass it already? Passed it already. There are not really a whole lot of instructions. So right there. So row 20 is the CPR instruction. Do you see on column A we have a binary bit pattern? So 0101 has to be there. Okay, so the most significant 4 bits, in order to specify a CPR instruction, it has to be 0101 constant. You cannot change that part. The other 4 bits are basically representing which register are we moving into and which register is providing the value to copy to the other one. So that's why I use XX to represent the 2 bits that you need to specify register X and YY are the 2 bits that you need to specify register Y. Why 2 bits? How many registers do we have?
We have 4 registers, so
Yep.
each register is represented by a 2-bit number.
Yep, exactly. So because we have 4 registers, we need 2 bits to specify one out of the 4 registers. So that's why we have XX to specify register X and YY to specify register Y. Oh, well, I'm supposed to be plugged in. Oh, there we go. I put the plug almost in, but it's not making electrical contact. But thankfully, the computer is pretty smart. It knows, hey, Jack, plug it in. Come on, push it. This is why the Apple plug is better, because it's all magnetic, right? So it just has to get close enough and go like, it just automatically connects. All right. So okay, let me just see if you guys know how to generate the actual opcode. So the instruction that we have is CPR AB. So what do you think the full opcode should look like? We know that 0101 has to be there. XX should be 00, and YY should be 01. So that means the opcode is 01010001, otherwise known as 51 in hexadecimal. Okay? So that one single byte that you store in RAM is going to specify the operation of copying register B to register A. Woohoo! So would you like to, hand assemble or do everything by hand? Look up this table, look up the instruction that you want to use, look up the actual binary bit patterns, figure out which part you have to fill in, and fill it in yourself. It might be fun to do it for like the first few instructions. After a while, it is not fun anymore. And that's why we have the assembler. That's what the assembler is for. The assembler looks at CPR A comma B, and it goes like, oh, I see that you want to copy register B to register A using this instruction CPR. So it automatically, quote unquote, automatically figures out that the opcode as a byte should be 01010001. That's the job of the assembler. Yep.
Are the opcodes universal or are they specific to the processor?
The opcodes are definitely specific to the processor. This is what they mean when they say your backward compatibility. So your Pentium processor today, your i7 processor today, is backward compatible all the way to the original 8086/8088 processor. So there's binary backward compatibility across the entire span of that family of processors. But this is definitely specific only to the toy processor. Okay, cool. So the next thing we're going to do is to go back to the assembler, and we'll try to see if the assembler does the job correctly. So you can click on the Assemble tab, which will give you stages of the process of translating. But you don't have to go through every single one. The one column that is actually important is going to be column P. Column P is giving you the exact hexadecimal representation of that byte representing this instruction. It's hexadecimal 51, which is exactly what we said it should be. So that is cool. Now, if you write a program and you want to test whether it works or not, if you're doing everything by hand, you're single clocking through the whole thing, you don't need anything else, okay? Because RAM is automatically initialized to all zeros. And they're basically no op and OP instructions, which does not do a single thing. On the other hand, if you have a very specific program and you say, I want to run this program, but I want it to stop at a certain point, okay, equivalent to having an exit in a C and C++ program, then you want a halt instruction so that it stops there, it doesn't go any further, okay? But in this case, I'm just going to single clock the entire thing, so it's not going to be a big deal. I don't need any instructions after this to stop, quote unquote, stop execution. So when everything is done, okay, you have an option. You can go to RAM file as a tab, and it looks like this. Okay, it says v2.0 raw, and then and then we only got one byte, which is 51. This is the content of the text file that you need in order for LogicSim to read something into a RAM file or ROM file. Okay. So in this case, this is not really needed, but I will show you how to do it anyway. So you go to download as, and you want to use either CSV or TSV. It doesn't really matter which one. I usually just use CSV, comma separated value, and we'll download this one as cpr.csv. Okay, how you want to name your file does not really matter either. Okay, so we save the file, and then we go back to LogicSim, which is right here. And then before you load the program in, I highly suggest that you click the reset button here, which resets the processor. But in addition to this, you can also go to simulate and reset simulation. Now, reset simulation is actually doing more than just resetting the processor itself. Because when you click the reset button in simulation, this is just actuating all the components here that has a connection to reset will be reset. But if I miss one component, that one single component is not going to reset. When you click simulate reset, that resets the entire simulation. There's nothing that will not be reset from that. But that is also going to be troublesome if you want to keep the same content in RAM. Because if you click the reset button, the button itself, it's not going to reset RAM because RAM has its own reset button, which is different from the other reset button. The idea is sometimes you don't want to clear the content of RAM, so I don't want that reset button to connect to clear of the RAM chip here. Okay. But if you go for the simulate reset simulation, that will reset the RAM content. So if you already have some useful program in it, it's going to be lost. Okay. So right now we can do a right click, load image, and then we go to the temp folder and pick out that cpr.csv file, click open, and now we have a single byte of 5.1. Now quite obviously this doesn't need to be done like this, right? Because I can just type 5.1 over here, go to edit content, and then just type 5.1 over here. It serves the same purpose. So when your program is really simple, there's no need to go through this entire thing to get the content in, but when your program is longer, this is handy. Do we have any questions about this entire process? So we are talking about the tool chain at this point, not even so much about the simulation or the processor itself, just the tool chain. How do we get the program in, how do we assemble, how do we get the file, and how do we load the assembled content back into the RAM. So we're good with that? Okay. So now we can execute the program. When you execute the program, it's going to be difficult with this particular screen because unlike some of you who has a 4K screen, which makes it easy to look at everything along with the HTML documents and whatnot, this one we have to scroll around a lot. Okay, so the bottom line, is somehow I need. Okay, let me go back into the register bank here. I'm going to copy the content of register B to register A. So before I run the program, it kind of makes sense to have some actual content in register B, because otherwise I cannot tell whether we actually copy the content of register B to register A when they have the same content to begin with. Okay, so we can change register B to something that is non-zero. Okay, 72 in hexadecimal. And if you want to, you can also change A to something that is non-zero as well. So we can use like F1, in register A. Just some random content that is not the same. Okay. If you want to debug the program and you want to know what is going on when you single-click the clock, you can go to simulate, then you can go to logging, and now you can move things from the left-hand side to the right-hand side in order to maintain a log of what is going on, what is happening as you execute a program. Now this can be very, very handy because what we can do at this point is we can go to we can go to register bank, and then we can say, okay, I want to keep track of register A, I want to keep track of register B, and outside of the register bank, I want to keep track of the program counter, PC. I want to keep track of the microcode pointer, which is U code. The U is an approximation of mu, the Greek letter mu, which in engineering means micro. So micro code is mu code, but because I cannot really type mu, I use u to approximate mu. That's actually pretty standard as well. So when you use when you try to type microsecond, a lot of times in engineering terms they use lowercase u s for microsecond. All right, so microcode pointer, yeah, go ahead. We want to copy that. Any other register that you want to copy is fine. Like the instruction register, we can copy that too. I'm just trying to see what else can be useful here. I think that's all that I need because we are not using the ALU. There's no computation involved in this process. If you want to, you can also copy the clock, which is just going to be a 0 and 1, because it's just flipping 0, 1, 0, 1 like that. Yeah, so I think that's it for now. You can go to File and specify a file to log to, which is kind of handy because this way, when you close Logisim, the file will still be there. So if you want to analyze the process of what happens when you run this particular program, the text file will still be there. And the text file is in tab separated value format, which means you can import that file back into Google Sheets if you have tools that you have written in Google Sheets to process the log file. So you can develop your own tool chain to help you debug your program. I would do that. I mean, after all, you're trying to make your own job easier when you're doing your homework assignment. Why not? So I'm going to give you the name. Okay, so in the temp folder, I'll just say this is cpr.log. Once again, the file name is not important. You don't have to name it as a log file. I just name it as a log file because it's just a nice, good convention to use. But I lied. It should be a TSV file because if you upload a TSV file to Google Drive, it will automatically offer to convert it into a spreadsheet. So that's why the extension is important if that's your intention. Okay, save it, close the window. Now we can single clock. So we go back to main, and the first question is, okay, where do we start? We got stuff everywhere, so where do we start? That's the question. Where we start is going to be here. This is where we start. In other words, the content of the ROM, the location that is being addressed at this point, is the starting point, because that dictates what the rest of the processor should be doing. So you always start with this part. Is that okay? So we have a pretty big number here. Okay, this is a 26-bit number, and that's why it takes a lot of hexadecimal digits. So 10800007 can split into all the individual bits. So you can track down these things and figure out what they're doing. Okay, to be more specific, the first thing we want to track down would be this wire, and just to figure out locally, what are we doing with this portion here. Is that okay? So what do you think the microcode pointer is going to do when I have a rising edge, when I have a clock? And by the way, I think the microcode pointer is sensitive to a falling edge and not a rising edge. So you can see right here, it is sensitive to a falling edge. It has to be opposite to the other registers. You'll see why later on, but this is sensitive to a falling edge. Okay, so what are we doing with this sub-circuit? Well, we know it is almost like a counter, right? We talked about the counter circuit, yep.
Does it just iterate through pieces of ROM?
Yep, exactly. But how do we know whether it is just incrementing or is it getting something from the bus from the other branch of the bus? How do we know?
Based on what comes in and instructions in RAM?
Well, the dictating factor is what is this wire specifying, right? So that wire is a 1, which means which input of this particular mux is going to feed to the microcode pointer. It will be input 0 or input 1.
So it's like, are we talking or are we listening?
Huh?
I said, are we talking or are we listening?
You as in the student?
No, the thing. Is it
I want you to be talking, yes.
to instructions, or is it doing what it wants to do?
I mean, right now, if I have a falling edge with a clock, is it going to increment, or is it going to be initialized based on the input 0 of this mux? That is the question. Okay, remember a multiplexer has multiple inputs and a single output. You have a selection pin or selection port, which is the gray dot, to specify which input becomes the output. So according to the state of this particular multiplexer right now, are we incrementing or are we changing microcode pointer according to the other input of the mux? We're incrementing, exactly. Because this one here, the one here, is specifying the input 1 of the mux to become the actual output of the mux. So we are already presenting 1 as the input to the microcode pointer. It's not changing because we are not seeing a falling edge yet. That is the only reason why microcode pointer is not changing to 1. But the 1 is already presenting itself as the input. Is that okay? All right. So this is cool. It means in the next falling edge, your microcode pointer will become 1, so that we can move on to the next slice of microcode to dictate what else should be happening in the entire processor. Okay, cool. So now we look at the rest of the processor, and we want to figure out, okay, what is it going to do here? Okay, so we look at, we look at the register bank because we just talked about it earlier. Do you think the register bank is going to do anything in the next rising edge? Is anything enabled? You look at RIEN, which is register input enable. That's a dark green wire. Okay, what does a dark green wire mean?
0.
It means it's a 0. Okay, so register input enable is not enabled. You look at register output 0 enable, dark green, right? You look at so the register bank itself is not going to be used at all at this point. What about the ALU, the arithmetic and logic unit over here? Is it enabled? Nope, because the EN port has a dark green line going into it, which means it is not enabled. We are not performing any calculations whatsoever. Okay. Are we updating the flags register? That EN is a dark green. We are not doing anything with that. Okay. Let's see, what else? Oh, the program counter. The program counter is kind of important. Are we updating the program counter? Nope. So for the most part, the processor is not going to do much. Okay. So what is enabled? So you basically just have to look at the bright green lines, because typically that tells you that something is enabled. So you track down those bright green lines. So you go like, okay, so this one is enabled, but it's not going to do a single thing because the program counter itself is not enabled. So the counting mechanism is not going to do a single thing. Here we have another green wire. Okay, so this green wire is basically saying whatever the program counter has is going. This particular wire is now connected to this wire. Okay, and is that significant? Let's see. So that wire turns out to go to the address port of RAM. Okay, and here we see a light bright green wire. RAM is selected. So we are the processor is telling RAM as a module, as a component, to say, pay attention. Okay. What operation are we specifying? LD has a bright green line. What does that mean? We have a read operation. We are reading from RAM. Which location is selected? Which location is addressed at this point? Location 00, which turns out to be the byte, the location of the byte that contains the opcode that we want to execute. Right? Okay. So do we need a clock falling edge or rising edge for read operation to do its job? Nope. So what does it? So if I click on this wire, what should I see? we should see 5-1. Or, depending on the binary pattern of 0101, 0001 should be on that wire. Does that make sense? Because the RAM module, the component is enabled, we are specifying a read operation, and the address is 0. So the content at location 0 should be on this wire. Okay, let me click it here. And sure enough, we do have 0101, 0001. When you run this on your own logic sim, you won't see 5-1 because I changed that in the class. So to change the base or change what is displayed here, instead of using a signed decimal representation, you have to go to, I think, project, and then go to options. And nope, that's not where. I cannot remember where. It's under window. Okay, so go to window, go to preferences, and then you go to window, nope, layout. Yeah, layout. So when you go to layout, the last two items is going to specify what is the one to the left-hand side of the slash and what is to the right-hand side of the slash. The first one in this case is binary. The second one in this case is hexadecimal. I strongly recommend that you change the second one from signed decimal representation to hexadecimal representation when you're trying to track down what the processor is doing. It just makes a lot more sense in general. So mine is changed already, and that's why we see what we are seeing. But if you have not changed yours, you're not going to see 5-1. Instead, what should you be seeing? 81. Good job. That was quick. 5 times 16 plus 1 is 81. Good job. Yep. Because the 1 is specifying how many 1s we have, the 5 is specifying how many 16s we have. So it's 5 times 16 plus 1, basically. Cool. Cool. All right. So now we have to track down this wire because if there's no reason for me to activate the RAM component and specify a read operation, I probably would not do that, right? So the fact that it is actually active, it's doing something, and is putting out the content of 5-1 onto this wire means it is probably getting utilized somewhere. So now we have to look at where this wire is going and what can potentially be updated. And you can see another bright green wire right here. See? And you can see how the data port is connected to the input of the instruction register, and this wire, which is connected to enable, is a bright green, which means it is a 1, which means this instruction register is about to be updated. Does it make sense? So this is what we need to do to understand how the processor works, is to track down all of these things starting from the ROM location itself. Okay? All right. So the instruction register is about to change its content from 00, which is by default because we just reset the whole thing, to 5-1 in hexadecimal. Okay. None of the other components is doing anything, so I think we are ready to clock it. Okay? I think clocking is Control T, but I can double check to make sure. So Control T is in fact tick 1s, which means we are changing the clock from 0 to 1. So Control T, ta-da! So you can see how the instruction register is now a 5-1. Is that okay? So the first thing we do is we use the program counter, PC, to specify which location we want to read into the instruction register. Okay? So now that we have that in the instruction register, what would the next clock transition going to do? What is that going to do? It's not going to do anything to the instruction register because the instruction register is rising edge sensitive. But we do have the microcode pointer itself that is falling edge sensitive. So when I Control T again, when the clock goes from high to low, the microcode pointer is going to go from 000 to 001. In other words, we're going to go to the next microcode slice to figure out, okay, so now what do we do with all of these components in the processor? Is that okay? So let's do another Control T, and sure enough, the microcode pointer is now incremented to a 1. And you can also see how the hexadecimal representation of location 000 and 001 of the ROM, they're quite different. Okay, the bits are kind of not the same. The 8 and the 8 are the same, but many of these bits are different. Okay, I can tell right here. Okay, this bit is different, and then the D specifies how many bits. D is 13, which is 1101. So we have 3 bits of difference just because of the D, a 0 to a D. And then the 7 changed to a 4 means 2 bits are turned off. Because a 7 is 111, a 4 is 100. So the least significant 2 bits are turned off because of this transition. In other words, things are different, okay? So we want to figure out, okay, so what is being different now? The first thing we know is this wire. This wire used to be 1. In other words, we are not incrementing the microcode pointer anymore. Okay, you can see how the result of adding, which is input 1, is not selected anymore. It is input 0 that is now selected. So now we want to say, okay, if input 0 is selected, where is that coming from? Input 0 is interesting because it is coming from a merger. The merger is merging a bunch of zeros to the instruction register. The tunnel instruction is coming from the instruction register up here. Okay, let me scroll up just a little bit. You can see that. You can see how the output of the instruction register is going to a tunnel called instruction, which is used down here. So what is that going to do? In other words, we know that this is 5-1 right here. This Y has 5-1, not surprising. So that means that 5-1 is going to be here. But what is going to be here? Right before it goes into the input of the multiplexer. Say that one more time?
You have this same number, but the zeros in front of it.
On which side? On the right-hand side or on the left-hand side?
On the right-hand side.
On the right-hand side, that is correct. Because the least significant 4 bits are forced to be zeros. Exactly, it is just like shifting it 4 times to the left. Okay, very good. Okay, so now we can click this wire and confirm that in fact it is like that. Yep.
Those are the operand bits?
Huh?
Were those the operand bits for this instruction?
It's part of the opcode. So the opcode part is still here. 0101 0001 is the actual opcode. But it's also having 4 zeros before it is used to update the microcode pointer. So the microcode pointer, when you reinitialize, quote unquote, reinitialize the microcode pointer, it always has the least significant 4 bits being zeros. Because we divide the ROM space into chunks of 16 locations, and each chunk of 16 locations is reserved for a particular opcode. So that's how we are doing indexing into the ROM to figure out which microcode is the starting point of the opcode that you're trying to execute. Is that okay? Mm-hmm.
So like the 4 bits that you added on, those are what we're using to index like
Correct.
The actual each part of each instruction.
Yep, exactly. So location 510 in hexadecimal is the address of the first slice in the ROM that represents the beginning of the CPR instruction. But to be more specific, it is CPR AB, because CPR DA is going to be different. Is that okay? All right. Okay, so the instruction register or the microcode pointer is not updating yet because this one is going to update on a falling edge. And right now the clock is low, so it's not going to update. Let's see what else we're going to do here. Because everything that has a green wire, a bright green wire, we have to pay attention. Ooh, this one has changed, right? The program counter did not have was not enabled. Now it is enabled. So when you look at any register that is enabled, chances are it is about to be updated. Okay. So now the question is, how are we updating the program counter? Okay. It's the same kind of setup. The input to the program counter has a multiplexer, so we can choose which input or how we want to update the program counter. So by looking at the state of the selection pin, or selection port of this multiplexer, how are we updating the program counter? Are we using input 0 or are we using input 1 to update the program counter? We're using input 0 because the PC mux itself is a 0. Okay. Does it mean that we are incrementing the program counter or are we changing it based on the other input to the multiplexer? We're incrementing. Very good. Because we are using input 0, this 0 here means we are using input 0 to update the program counter. But this wire is coming straight out of the adder and it has a value of 1. In other words, in the next rising edge, program counter it will increment to 1. Is that okay? What else is changed in this picture? Let's go to the RAM because RAM was used earlier and you can see that it is not used anymore. The purpose of the previous cycle is to read the instruction from RAM into the instruction register. Once that is done, I don't need to use RAM anymore, so I'm turning it off. Okay? Now we still have the RAM load of 1, but that's not going to do a single thing because the RAM itself is turned off, it's disabled. So are we okay so far? Okay? So when we actually have another clock transition, the clock currently is a low. When we have the next clock transition to a 1, we can expect the program counter to increment to 0, 1. We are not expecting the microcode pointer to update just yet because the microcode pointer is updated on a falling edge. Okay, so here's Control T, and you can see how the program counter is now updated to 0, 1, so that the program counter is always pointing to the next byte to read. Is that okay? So the moment you are done with reading whatever you need to read, which is the opcode, it always auto-increment so that it will be ready for the next instruction. The microcode pointer is not updated yet, but when I do Control T, it's going to update. So let's focus on the microcode pointer at this point. We know the input to the microcode pointer is already 510, so on the falling edge, we are expecting the microcode pointer to update to 510. Okay, so Control T, sure enough, it is now 510 in hexadecimal. So now we go to the ROM again, and then we can get the content of that location is 1500990. What does that mean?
From the output to the processor.
Exactly. It specifies all of these control signals to the rest of the processor. Okay? But what do you think we should expect? Because we know that this is corresponding to the mnemonic of CPR AB. So what do you think we are expecting to be enabled at this point? Something in the register bank, right?
Yeah.
Okay? So we'll check out the register bank first. Well, before we do that, we just want to, because we're already here, what do you think the microcode pointer is going to do in the next falling edge? Is it going to increment, or is it going to get another instruction opcode? Is a 1 to the selection port, which means we are using input 1 to serve as the output. Input 1 is this wire, which is coming from the adder. So we are basically setting it up to just increment. Okay? And now we go up a little bit. The program counter is not changing because we are not updating the program counter. We are done with using the program counter for now. When you go up here, you can see how the register bank input enable is a 1, and register output enable is also a 1. Okay? Now we want to see whether we are selecting the right registers. Okay? Which register was supposed to be updated? Register 0, right? Register A, which is 0, 0. So we want to check RI cell or register input selection. I cannot click it. But this is supposed to be 0, 0. Which register provides the value? Register B, which in binary is 0, 1. So we are expecting RO0 cell to be a 1, 0, 1. And once again, I don't think I can click it. Oh, I can. Huh? Sorry?
I was gonna say try clicking on, because it has that one selected, maybe the blue ring is throwing
Yeah.
off why you can't click on that wire if you like maybe select.
I cannot. I cannot click on this one, but I can click the other side of the tunnel. So RISEL is right here, and that in fact is 0, 0. Okay? Alright, so if you're not buying, this is going to get the operation done in the next rising edge. We can now look into the register bank. The cool thing about LogicSim is when you look into a subcomponent, the state is the same as the outer picture. In other words, it is reflecting what is the current state actually in the outer circuit. So right now we have this particular decoder turned on, enabled, because of this one. We have 0, 0 as the select, the input select, and that's why this wire, Y0 or output 0 is a 1, which means we are selecting register A. The enable of register A is now a 1, which means in the next rising edge, it can be updated. We can also see what data is being used to update it. It is 0, 1, 1, 1, which is a 7, 0, 0, 1, 0, which is a 2, so 7, 2 is what we are going to use to update A. Where is that coming from? It's coming from register B. So we want to see why that is the case. This is register B, why is it 1, 0, 1, 1, 1, 0, 0, 1, 0? It has to do with how we select the, which input becomes the output of this multiplexer. So the select of register output 0 is 0, 1, which means we are not using input 0, we're using input 1 to be the output. Input 1 comes from register B, and that's why we have register B serving as the output of register, output register 0 of the register bank. But how did that get routed back to the input? You cannot see it from the register bank itself. So we look at register out, we look at out 0, it is the right value, but then we have to look at this multiplexer. This multiplexer has to do its job right to route it to the right place. So we can look at register output 0 demux, which is this wire. It is selecting 2. This is 0, this is 1, this is 2. So we're looking at this wire here. So this entire wire has 7, 2 as its content. It goes to many places, including the input 0 of this particular multiplexer. And the input 0 of this multiplexer is actually serving as the output of the multiplexer, which then goes into the input of the register bank. And therefore, we now complete the entire path from one register in the register bank as the output back to the input of another register of the same register bank. So do you see how those wires, basically establish the path between the components that we need to connect? And that's the microcode. The microcode is basically just instructions to do all of this stuff. Okay, so let's go back into the register bank, because the next rising edge, we should see something. So we'll do a control T at this point. When we do another control T, the clock would go from 0 to 1. See how this is the clock, it is currently a 0. So when we do control T again, it would go from 0 to 1, which means register A will now be updated to 72 in hexadecimal. So control T, and you can see how it is updated. Cool. Then we go back to main and go like, okay, now we are going to see another falling edge. And falling edge only affects the microcode pointer. Okay, none of the other components is sensitive to a falling edge. The microcode pointer is the only one that is sensitive to a falling edge. So how are we updating the microcode pointer? Well, we talked about this already. It's just going to increment. Okay, so control T again, and now the microcode pointer is back to a 0. That doesn't make sense. Incrementing from 510 should go to 511. How come it went all the way back to 0? Well, I'll tell you why. Because we are not flies, the insect. Why do you think I said that? For a very, very brief moment, it was 511. But then it changed to 510. It changed back to 000. So now the question is, what is specified at location 511 that would cause the microcode pointer to go straight back to 0, 0, 0 so fast that we cannot observe it. Now remember, I'm single clocking everything using Control T, and there's only so much, I can only click it so fast, right? I click it once, and to our eyes, it just went straight back to 0, 0, 0. It never went to 511. But in reality, it did go to location 511. It's just that the moment it got to 511, bam, it goes back to 0, 0, 0. So just by looking at this picture here, what do you think can cause that to happen? There's one wire here that can do that. The microcode pointer has a particular port that can cause it to go straight back to 0 without clocking. The reset port, which is this wire over here. Then you go like, well, isn't this wire going to connect to the global reset pin of the entire system? Not this guy. So when we track down this wire, okay, so we'll track it down. It comes from this this OR gate here. So this OR gate is basically saying the system-wide reset will reset the microcode pointer. Not a problem because it's an OR, right? But there's another way to set it. So we track down the other wire, which is this one, and it goes to bit 25 of the ROM. So that means, so you start to suspect, right? Bit 25 of location 511 must be a 1. That is why the microcode pointer went straight back to location 0, 0, 0 without even clocking.
And it is the one because we see it over there. That's me.
We can examine the
Or no, that's
locations.
0, 0. If we go back to the instruction of 5.
Yeah, so we can look at the content. So we can go to edit content, and then we can now go to location 510. So location 510 is right here, and this is the one that we're questioning. Okay, it's 2 followed by 6 zeros. Okay, does that specify bit 25? One hexadecimal digit is 4 bits, 4 zeros, right? We have 6 zeros, so we have 1, 2, 3, 4, 5, 6 hexadecimal zeros, which translates to 24 zeros in binary. Well, but that only accounts to up to bit 23. Bit 24 would look like a 1 from the perspective of hexadecimal, and bit 25 looks like a 2. So this 2 here, indeed, specifies that bit 25 is a 1. That is why we did not see the microcode pointer staying at 511, because the moment it got to 511, this bit says, oh, go ahead and reset the microcode pointer back to 0. And it happened so fast that we couldn't see it. Is that making any sense? But why? Why are we going back to location 0, 0, 0? What did it do? We already examined what location 0, 0 and location 0, 0, 1 would do. So what are we setting up the processor to do at this point? To read the next instruction, exactly. That is called the fetch cycle. Okay, the fetch cycle is to go to RAM to read in the next opcode, and then location 001, which is copying the opcode and pad it with 4 zeros and put it into the microcode pointer, is called the decoding process. So we fetch, we decode, and then when we got to location 510 and actually perform the copying thing that CPR is supposed to do, that's execute. And then when you're done executing, you go back to fetch. So it's fetch, decode, execute, and then back. So are we doing okay so far, tracking down how instructions execute in this processor? It's tedious, okay? It is extremely tedious because there are many, many moving parts. But you know how to track down the moving parts. You look at all the ENs first, okay? The enable pins are the most important ones. And you always start with the ROM because the ROM is dictating how everything else is supposed to behave. Is that okay? Yep.
Sorry,
sorry, I think you repeated again. You said fetch, then decode, then.
Yeah, fetch, decode, execute,
That's
and then back to fetch. Yep.
So as soon as it was done with the location of 5100, it moved over to the next location, which is the 2.
Right.
Which has the 2, and the 2 means that it.
Yep, it goes all the way back to location 000 because we're getting ready for the next instruction.
Gotcha.
So here's the next question. We only specified one instruction, right? The 5-1. Now we are getting back to location 000. What is it going to do? We kind of know what it's going to do because we know that it will try to it will attempt to execute the opcode of 00. So now the question is, what is that going to do? So what you need to do now is to disassemble the program. In other words, you look at the actual binary bit pattern and you go back and figure out what mnemonic corresponds to the binary bit pattern. It's the reverse of assembling, so that's why it's also called disassembling. Is that okay? So what do you think 0000 in hexadecimal is corresponding to as a mnemonic? No op. As it turns out, it is just no op. So if you go back to the instruction opcode table, and if you scroll up a little bit, row 7 states that the no op instruction has exactly the bit pattern of all zeros. Because it really is just fetch, decode, there's no execute. There's nothing to execute. That's why it's no op, nothing to do. So when you have a bunch of no op instructions, it's just alternating between fetch, decode. But the decode gets it back to the fetch. And then it's ready for the next instruction. But this is where you're supposed to say, I'm not convinced, show me that, right? So we do the control T, control T, control T, and then you go to the next one, and it just keeps going like this. All the way until we get to location FF or 255, then it overflows, it goes back to location 0, and it will re-execute 5-1 at that point. So the program does not crash when you run out of in locations to execute, it just wraps around. Yep.
That's why you have like an explicit halt, is that if you don't have a halt, it'll move
Yep,
around.
it just keeps going. If we had a halt instruction, then it would just be stuck at the halt instruction. Then it doesn't go any further. Yep.
So basically this processor is just designed just to go forever, pretty much. Just keep moving.
Until you hit a halt instruction, correct. So are there any questions about this entire process? We just executed one particular instruction, CPR AB.
So like for the actual microcode in the ROM unit, do you just break up each like set of bits per instruction per microcode into a configuration for the
Yep.
rest of the CPU?
Yep. Which is not, which is tedious. Okay, so let me show you the actual content, or scroll through the content of the ROM. Okay, so we'll go to edit content again, and you can see most instructions have something for location 0 of those 16 locations. There's a whole bunch of instructions, there's a whole bunch of locations that are zeros at this point, which means we have spare opcodes at this point. We can implement additional operations. And then there's a whole bunch that are actually occupied like this. And then we have pockets of sections that are not used. And then we have some other opcodes over here. And you can probably imagine to specify the entire content of the ROM is rather tedious if you are to do this by hand. So the question is, do you think TAC is going to do this by hand?
No.
So this is not done by hand. I actually wrote programs to generate all of these patterns on an instruction by instruction basis. And it's a single. Okay, let me show you which part I'm talking about. You can download this tool and play with it too if you want to. So you go to the processor subfolder. There is a file called opcodes.zip. There we go. This is the file. So once again, it's a zip file. It unfolds to its own folder this time. So let me just download it and show you what it looks like. So we say download, and we'll put it into the temp folder, and then switch to the command line, the one that you can see. Okay, so we go to opcodes, and the first thing, I'm just going to list all the .c file. And what do you notice about most of the names of these .c files? They're named after the mnemonics of the instructions. Cool. Yep. So when you look at each one, let's look at one that is kind of interesting, add. Okay. Add is interesting because how many variants do we have with the add instruction? Remember, add AA has one opcode, add one AB has another opcode. So how many opcodes correspond to just add? 16, exactly, because we have 4 choices for the first register, we have 4 choices for the second register, and they are independent. So that's why we have 4 times 4, which is 16. Okay? So we now look at the actual code of add.c. It is data driven. So this is the kind of data that is driving the engine. The actual code is just this much. It is going to generate all 16 variants of the add instruction. This stuff here, okay, so when you look at slices, each number or each field of slices is corresponding to one wire coming out of the splitter out of the ROM. And it's ordered in, I think, the most significant bit all the way down to the least significant bit. And that's why you can see the second slice has a 1 here, because this one corresponds to bit 25. It's the most significant bit. So if you want to know how it is magically generating all the variants of XX and YY, it has to do with the use of these constants, XX field, YY field, and so on and so forth. That's how I can make it look easy when in fact it generates all the variants. It also has 2 slices. The first slice is coming from index 0. The second slice is coming from index 1. And I cannot remember. Oh, 80, by the way, is the base code of the add instruction, which is basically saying 1000 has to be the most significant 4 bits. And then the other 4 bits depends on which register are you adding to which other register. Okay. And then this 0 is the offset. This specifies the first slice of the 16 possible slices for that particular opcode. This means it is the second slice of those 16 possible slices. So there are, this is all written in plain C, by the way. So if you look at the other files, I think it's rom.bin.c. This is parsing the input, which is the kind of input that you saw earlier when you load the content into Logisim. This is the parser that will parse the input. And then we have, yes, I wrote a really long function. And this is the reverse. So basically what I do is I read a CSV file into a table, and then I perform the operations, whatever the executable does, and then it will spit out another ROM file with the addition of whatever instruction I'm implementing with this file. So if I need to make any changes, okay, so if I want to regenerate all the instructions as a ROM file, this is all I need to do. Make all.rom, I think. All.rom. Oops. Ooh, not installed. Okay. That can be arranged. This is why I like Linux. If you know the package name, it's just a matter of, okay, let's install it now. It goes to the repository, find out exactly which version is compatible with whatever I have installed here, and that's all I need. It is up to date. Okay, let's make clean. And then make again. Okay, so the last instruction is what concatenates all of the opcodes together. You can see it, or you cannot really see it. But all of these programs, all of these are individual executables, but they're all piped from one to another. So the output of one becomes the input of the next one, and each one is adding its own microcode slices on top of whatever was specified earlier. So that's why it is one gigantic piped sequence to generate the final result.
So you're just like adding a bunch of binaries together then?
Yes, it's almost like that, except it is kind of more scalable because I'm using standard in, standard out, so it doesn't need temporary files at all because you're using the pipe to say, okay, whatever the input is to me, I'm just adding something to it, and then I'm passing it on to the next person. So if you are responsible for JMP, okay, you take whatever is in the input, which may have a bunch of opcodes already implemented, you're just adding your own instruction, which is the JMP instruction. So when you're done, that ROM image has one or a few more locations specified. So you turn it back into a ROM file, and then you pass it on to the next executable, which may be responsible for CMP. So CMP says, oh, I got 16 variants. You're going to specify a bunch of bytes. Then you pass it on to the next person. So each person is passing it's whatever it receives, plus the instruction is implementing, and then pass it on to the next person. Yep.
So wait, are you like passing the actual empty ROM file at the start?
Yes.
And then totally adding to it?
Yep.
via standard in and standard out to the
That's why this starts the whole thing. There's an empty ROM file to begin everything. And then the eval is actually what is doing the piping, because I use the echo. The echo stops here, and it has to go through sed in order to include the vertical bar for the pipe, and then the output of sed becomes the actual bash command. So I'm using the backtick to treat it as its own command. Yep. So it took me a little bit of time to figure out, all of this stuff to make it really easy. So at this point, what that means is if I need to make a change to, let's say JMPI, let's say I had a bug or something. Oops. I need to look at the .c file, right? Okay. So I'm not actually going to change it. So I'm going to just change the file, change the timestamp of the file, and all I need to do is to type make again. It will recompile just whatever is necessary, and then regenerate the file that I call all.rom. So all.rom is the actual file that contains the pattern to fill up the ROM component itself. And the content is really just a text file, but it looks really ugly because it's generated by a machine. So it looks like this. You go like, what are those @ signs? Well, the @ signs is just one single huge long line. That line has 3,845 characters, but it's one line.
It's a one-liner.
Huh?
Technically, it's a one-liner though.
It is a one-liner, exactly. So this is the tool that I use to generate additional instructions. But understanding this tool can be helpful to understand how the processor itself works. Okay, so that's up to you to choose whether to look into this or not. Yep.
It looks like after each instruction, you always have the 2 followed by the 0s following it. So whatever instruction it is, it's always going to jump back to the start.
There's one instruction that is not followed by the 2 followed by all zeros.
Is that the first one?
Nope, it's the hold instruction.
Oh, okay. I mean the second.
But you're correct. Every single instruction, every single useful instruction is followed by the 2 followed by all zeros.
So as soon as it's done, it's just hope.
Right. Now it is just that the processor is designed to do it efficiently, so that I never really need more than one actual slice of microcode to get things done. Now, given that the instructions that we implement are really simple, so if I go back to the opcode table, you can see that we only have very few instructions. We have, I think last time we counted, right, 30 something instructions. Does anyone remember? Okay, so if I go to the assembler thing, go to the mnemonics part, that is an easy way to count because we just count from row 1 all the way up to row 31. So we have 30. These two are not really implemented, neither is add I. So 28 is the actual number. We have 28 individual mnemonics, which is not many. I mean, that's really small, a small number compared to many architectures. Cool. Compared to the Intel architecture, which probably has easily upwards of 100 or 200 different mnemonics. That's a monster. But why are we going to simplistic design? Other than I don't want to make this too complex. But we talked about the RISC architecture versus the CISC architecture, right? So do you guys remember what is the strength or the reason why we are leaning on RISC architectures?
Power efficiency.
Huh?
Power efficiency.
Energy efficiency, yes. So energy efficiency is the reason why we are preferring RISC architecture instead of CISC architecture. Just remember that example, you have a LAN party and you cannot get rid of all the heat in the room. So if you have a LAN party and you're playing any game that needs like 5 people in the team and you have 5 gaming computer in the team, there's no way you can get rid of all the heat. The question is the computer going to die first or are the gamers going to die first? Pass out, or not say not die, but pass out, KO. I'm guessing the computers will go first. So is that okay so far? So we have 5 days before we meet again on next Tuesday, and many of you probably do not have anything to do because the assignment is due today. There's nothing assigned at this point. So what I want you guys to do is to repeat the experiment that I just did, okay? But don't follow the way I track down everything. Do it on your own. And the key, oops, I just passed it. So the key is to start with the ROM module, okay? The output of the ROM is what is controlling everything else, how to operate. And do it on a clock by clock basis. Control T, rising edge, Control T, falling edge, Control T, rising edge, Control T, falling edge. And you can try out different instructions too. Okay? Nothing is going to explode. Nobody's going to get hurt. So try it out. Okay? That's how you study for this class is you get the whole thing, you try it out, you study and find out how it works.